All right, so let's look at a couple of shear and moment diagrams, and we'll have you do these yourself. And so here I've got kind of my rules, what I'm thinking about. 1, 2, 3, 4. For all of these, first thing, what you got to do, you've got to do the statics, right? You've got to find the forces at if there's a roller, if there's a pin, if there's a wall. We did that in statics, so you can't forget that. The one thing that I will say is that my students generally sometimes would forget that at a wall, it's a fixed support, right? So at a wall, you've got a force in the Y, and you've got a moment. Anyway, don't forget about that moment at the wall. So you got to do the statics, then you got to do the shear diagram. I think about it like hopping on the shear diagram and getting pushed up and down immediately or up and down gradually, ending up at 0 so that you can hop off. Then between the shear diagram and the moment diagram, I like to calculate the area under the shear diagram. Positive area above, negative area below, and then I'll use that when I go to the moment diagram. I'm, getting pushed up and down immediately by concentrated moments and getting pushed up and down gradually by the area under the shear. All right, so those are kind of my rules. Let's see. So you can kind of see these. And here I did put correctly that clockwise pushes the moment diagram up. Counterclockwise pushes the moment diagram down. Make sure you start and end everything at 0. And then 5, just double check that everything makes sense, right? V is the integral of the loading, M is the integral of V. Make sure that the maximum moment is where V is equal to 0 because that's where this slope is 0. And don't forget about these, make sure that it goes from nothing to constant to linear to parabolic to cubic, right? Because we're taking integrals, that's what it's going to be. So if you got nothing here, then the one below it, you're going to be flat or constant. The one below it, you're going to be linear. So if it starts with a constant distributed load, then your V is going to be X and X squared. So just make sure it goes kind of in this order because we're taking integrals of everything. All right. So let us start with this one. So we'll start with the statics. So we've got a fixed support at the wall. We'll draw that AY, draw that MA. Sum of the forces in Y is equal to this, is equal to 0. So we've got AY is equal to 18. And then we'll sum the moments. We can sum moments about any point, but I'll sum moments about A. So we've got that MA, we've got that 10 times 2 and the negative clockwise rotation, we've got the 8 times 5 in the negative. We've got that 15, which is negative. So we'd get MA 75. That would be in kilonewton meters. So anyway, number one, you got to do the statics. You got to do that statics right. If you don't do the statics right, then you're probably not going to end up at 0. And that's kind of a sign that maybe go back and do that statics again. So let's do the shear diagram. Think about you're like this little person and you're going to hop onto the shear. So I'm about to get on. First thing I see is that 18 up, so that pushes me 18 up. So here I'm at 18. Then I just walk along flat, right? There's nothing between in that first 2 meters, so just stay at that 18. Then I go down by 10, so I was at 18, now I'm at 8. Then I just keep walking, nothing's happening, so I go along flat, and then I go down at 8 and I get to 0. You've got to get to 0. If you don't get to 0, then you probably did something wrong with the statics of the problem, or maybe you did something wrong with the shear diagram. So now let's go to the moment. But actually, before we go to the moment, let me calculate these areas under the curve here. So break it up into sections, break it up into rectangles or triangles, whatever you need to do. So this section right here, base times height. Base is 2 meters, height is 18 kilonewtons. So here we've got 36 kilonewton meters is the area under that curve. It's positive because it's above the axis. This one, the area under this curve, it's a rectangle, base times height, so 3 times 8. 24 is the positive area under the curve in that section. So we'll use those areas under the curve for our moment diagram. So here is our moment diagram. Start at 0. And then immediately I see that 75, right? Immediately I feel that 75. Counterclockwise pushes me down. Counterclockwise pushes me down. A counterclockwise moment pushes me down. I think I wrote that wrong on the other page. But counterclockwise moment pushes me down. All right, then the area under the curve, right? The area under the curve is 36, so I'm going to change by 36. So I was at negative 75. I'm going to change by 36. I'm going to up 36. So now I'm at negative 39. How do I go that? How do I get there? Is it curved? Is it linear? Well, v is the slope of m, so the slope is just 18. Slope is 18, slope is 18, so it is linear. All right, and then I'm at negative 39. I need to go up by 24, so I go up from negative 39 to negative 15. I go linearly because v is the slope of m, and then I get to 0, right? Because the last thing I see is this 15 Newton meters, this 15 Newton meter moment right here. So now just double check that everything went to 0, right? Everything started from 0, everything ended up at 0. Make sure that it makes sense, the order that we're at. Make sure it goes from, right, at the loading, we had nothing. So then at the shear diagram, it is flat. And then so at the moment diagram, it is a linear in the x, right? We've got nothing, flat, and then a linear x, right? Nothing, flat, linear x. Make sure, because we're kind of taking the integral of everything. So at the end of it, just make sure everything goes to 0, make sure v is the slope of m, and make sure everything makes sense.